Starting with absorption. Absorption loss is related to the material composition and fabrication process of fiber. Absorption loss results in dissipation of some optical power, as here in the fiber cable. Although glass fibers are extremely pure, some impurities still remain as residue after purification. The amount of absorption by these impurities depends on their concentration and light wavelength. Absorption is caused by three different mechanisms. That is, absorption by atomic defects in the glass composition, extrinsic absorption by impurity atoms in glass nets, intrinsic absorption by basic constituent atom of fiber. So, what is this extrinsic absorption and intrinsic absorption that we are going to see in detail? And these are what the types or the different mechanisms of absorption which is always asked in examination. So, absorption by atomic defects. Atomic defects are imperfection in the atomic structure of the fiber materials, such as missing molecules, high density clusters of atom group. These absorption losses are negligible compared with intrinsic and extrinsic losses. So, atomic defect can be neglected as compared to intrinsic and extrinsic losses. The absorption effect is most significant when fiber is exposed to ionizing radiation in nuclear reactor, medical therapies, space mission, etc. The radiation dents the internal structure of fiber. The damage are proportional to the intensity of ionizing particles. This results in increasing attenuation due to atomic defects and absorbing optical energy. The total dose a material receives is expressed in radian. This is the unit SI. This is the unit for measuring radiation absorbed in bulk silicon. 1 radian silicon or silicon is equal to 0.1 joules per kg. The higher the radiation intensity, more the attenuation as shown. So, as the radiation is increasing, attenuation is going on increasing. Exponential graph, it is showing attenuation versus radiation. Extrinsic absorption, the second type of absorption, extrinsic absorption. Extrinsic absorption occurs due to electronic transitions between the energy level and because of charge transitions from one ion to another. A major source of attenuation is from transition of metal impurity ions such as iron, chromium, cobalt and copper. These losses can be up to 1 to 10 dB per kilometer. The effect of metallic impurities can be reduced by glass refining techniques. Another major extrinsic loss is caused by absorption due to OH, hydraulic ions, impurities dissolved in glass. The vibration occurs at wavelength between 2.7 and 4.2 micrometer. The absorption peaks occurs at 1400, 950 and 750 nanometer. These are first, second and third overton respectively. So this figure shows absorption spectrum for OH group in silica. Between this absorption peaks, there are regions of low attenuation. So this is a wavelength where wavelength when it is increasing, the attenuation rate which is less at 750 nanometer, the attenuation is high. At 950 nanometer, attenuation is again high, and at 1400 this attenuation is high. Rest all attenuation is low. Intrinsic absorption. Intrinsic absorption occurs when materials is in absolutely pure state, no density variation and inhomogeneity. This intrinsic absorption sets the fundamental lower limit on absorption for any particular material. Intrinsic absorption results from electronic absorption bands in UV region and from atomic vibration bands in the near infrared region. So, intrinsic absorption results from electronic absorption band in UV region and from atomic vibration bands in the near infrared region. The electronic absorption bands are associated with the band gaps of amorphous glass material. The absorption occurs when the photon interacts with an electron in the valence band and excites it to a higher energy level. UV absorption decays exponentially with increasing wavelength. The infrared region above 1.2 micrometer, the optical waveguide loss is determined by presence of the OH ions and inherent IR absorption of the constituent material. The inherent IR absorption is due to interaction between the vibrating band and the electromagnetic field of optical signal. This results in transfer of energy from field to the band, thereby giving rise to the absorption. This absorption is strong because of many bonds present in the fiber. Attenuation spectrum for the intrinsic loss mechanism in pure germanium is shown below. So this is attenuation spectrum for intrinsic loss, where photon energy in electron volt, when it is increasing, we can have this losses in dB per kilometer. And this is wavelength. So this region after 1.5 and the wavelength of 5 is showing us absorption, and this region is showing UV absorption. The ultraviolet loss at any wavelength is expressed as alpha UV is equal to 154.8 divided by 46.6 x plus 60 into 10 raised to minus 2 into e raised to 4.63 divided by lambda, where x is the mode fraction of GeO2, lambda is operating wavelength, alpha UV is in dB per kilometer. The loss in infrared region above 1.2 micrometer is given by expression alpha IR, that is equal to 7.81 into 10 raised to 11 into e raised to minus 48.48 divided by lambda, 38.45 divided by lambda. The expression is derived for GeO2 SiO2 glass fiber. Okay, so this is all about absorption. We have seen three types of absorption: atomic, extrinsic and intrinsic, right? Atomic effects, extrinsic absorption and intrinsic absorption. So moving further with Rayleigh scattering loss. Scattering losses exist in optical fiber because of microscopic variations in the material density and composition. As glass is composed by randomly connected network of molecules and several oxides, for example SiO2, GeO2 and P2O5, these are the major cause of compositional structure fluctuation. These two effects result to variation in refractive index and Rayleigh type scattering of light. The Rayleigh scattering of light is due to small localized changes in the refractive index of the core and cladding material. The core and cladding, everything will be clear in your first module. Fiber, if you see the design of fiber, it consists of core and cladding. Core is the main inner part where the signals travel. Core is covered with cladding. Both are made up of glass, but the material temperature where it has been designed is different for core and cladding. These are two causes due to manufacturing of fiber, during the manufacturing of fiber. So refractive index plays very important role for scattering. The first is due to slight fluctuation in mixing of ingredients. The random changes because of this are impossible to eliminate completely. The other cause is slight change in density as the silica cools and solidifies. So because since it is made up of glass material, it is maintained at a particular temperature. So first it gets cooled and then solidifies. When light ray strikes such zones, it gets scattered in all directions. The amount of scatter depends on the size of discontinuity compared with the wavelength of light. So the shortest wavelength, highest frequency, suffers most scattering. The figure below shows graphically the relationship between the wavelength and Rayleigh scattering loss. So this is how you can see as soon as the wavelength increases, you can say shorter the wavelength, higher is the frequency and your loss is also high. But wavelength when it is increasing, your loss is going to decrease. So this is what scattering loss is. So the scattering loss for single component glass is given by the situation. Single component glass. This is just a theoretical equation. Till now, no numericals have been asked to calculate this thing. So alpha sat is equal to 8 pi raised to 3 upon 3 lambda raised to 4 into n square minus 1 the whole square kb t f beta t nippers. Nippers is the unit here, where n is refractive index, kb is Boltzmann's constant, beta t is isothermal compressibility of material, tf temperature at which density fluctuation are frozen into the glass as it solidifies fixed to temperature. Another form of equation is alpha sat is equal to 8 pi raised to 3 upon 3 lambda square into n raised to 8 t square kb tf beta t. So your alpha sat is equal to 8 pi raised to 3 upon 3 lambda square into delta n square the whole square into delta v, where delta n square is mean square refractive index fluctuation and delta v is volume of fiber. So the equation has been modified in this term. So multimode fibers have higher doping concentration and greater compositional fluctuations. The overall losses in the fibers are more as compared to single mode fibers. My scattering is another type. My scattering loss. My scattering loss, if the size of the defect is greater than 1/10 of the wavelength of light, the scattering mechanism is called my scattering. If the size of defect is greater than 1/10 of the wavelength of light, the scattering mechanism is called as my scattering. Linear scattering also occurs at inhomogeneities, and this arises from imperfection in the fiber's geometry, irregularities in the refractive index, and the presence of bubbles, etc., caused during manufacture. Careful control of material or manufacturing process can reduce the my scattering to insignificant levels. So this Rayleigh scattering and my scattering are a type of linear scattering laws. Now moving further for non-linear scattering laws. Non-linear scattering laws occurs when frequency is changed during optical power transfer. The two types of non-linear scattering are stimulated Boolean scattering and stimulated Raman scattering. These are non-linear scattering losses. The stimulated Boolean scattering is a cause of concern in long-distance system, in wavelength division multiplexing systems, and remote pumping of an erbium doped fiber amplifier (EDFA) through a separate optical fiber. If you want, you can go through the book Senior, and they give more details about stimulated Boolean scattering as well as stimulated Raman scattering. The stimulated Raman scattering creates problem in wavelength division multiplexing system. Moving further with bending loss. Bending loss, losses due to curvature and losses caused by an abrupt change in the radius of curvature are referred to as bending loss. Losses due to curvature and losses caused by an abrupt change in radius of curvature are referred to as bending losses. The sharp bend of a fiber causes significant radiative losses, and there is also possibility of mechanical failure. This is shown here. So this is a core of the fiber where the light rays is traveling, but as soon as there is a bend, this rays may escape, right? So normally the ray should bend like this, but because of bend, the ray escapes. As the core bends, the normal will follow it and the ray will now find itself on the wrong side of the critical angle and will escape. The sharp bends are therefore avoided. The sharp bends are therefore avoided. This is very important. The sharp bends are therefore avoided. The radiation loss from a bent fiber depends on field strength of certain critical distance xc from fiber axis where power is lost through radiation. The radius of curvature R. The higher order modes are less tightly bound to the fiber core. The higher order modes radiate out of fiber firstly. For multimode fiber, the effective number of modes that can be guided by curved fiber is given by expression N effective is equal to N into 1 plus alpha plus 2 upon 2 alpha delta into 2a by R plus 2 upon 2 pi cube pi 3 2 alpha 3. I will just check out this equation and let you know. Alpha is graded index profile. Delta is core cladding index difference. N2 is refractive index of cladding. K is grade propagation constant 2 pi by lambda. N delta N infinity is total number of moles in the straight fiber, where N infinity is equal to alpha by alpha plus 2 into N1 Ka total square into delta. So there are two types of bending. One is micro bending and macro bending. Micro bending is a loss due to small bending or distortion. This small micro bending is not visible. The losses due to this are temperature related, tensile related, or crush related. The effect of micro bending on multimode fiber can result in increasing attenuation depending on wavelength to a series of periodic peaks and roughs on the spectral attenuation curve. These effects can be minimized during installation and testing. This figure illustrates this microbending. This microbending are internally taking place, where some manufacturing defects like curvature takes place, because of which the core and cladding rays may get escape. So during manufacturing, whatever defects was been done is always being tested when it is being implemented. Macro bending. The change in spectral attenuation caused by macro bending is different to micro bending. Usually, there are no peaks and roughs because in a macro bending, no light is coupled back into the core from the cladding, as can happen in the case of micro bendings. The macro bending losses are caused by large-scale bending of fiber. The losses are eliminated when the bends are straightened. The losses can be minimized by not exceeding the long-term bend radius. The figure illustrates this. The long-term bend we need to avoid. Here, the losses will be avoided if this wire is made straight. So that's all for today. Thank you.